Hello everyone, my name is Sokol Celo and I will present the paper Lateral Collaboration in MNEs as Complex Adaptive Systems. The paper builds theory about lateral collaboration by modeling the MNE as a complex adaptive system. It applies the NKC methodology and the rugged landscapes to run computer simulations and uses their results to advance three propositions. Previous research has emphasized the benefits of increasing the level of lateral collaboration with MNEs as a way to leverage the knowledge generated in dispersed locations. On the other hand, there are also benefits to managing the MNE as a differentiated network, with subsidiaries playing specialized roles. These two sets of arguments seem to suggest that there is an optimum level of lateral collaboration, but what determines that optimum is an open question. Also, it is unclear how lateral collaboration optimization strategies differ between the MNE and subsidiary level. I argue that a view of the MNE as a complex adaptive system helps answer these questions. I see the MNE as a two-tier complex adaptive system composed of subsidiaries which, while pursuing their own interests, adapt and co-evolve with other units. MNE strategy emerges from their joint actions. At the MNE level, the effect of lateral collaboration of MNE performance materializes in two ways: relative to within subsidiaries interactions or as part of the total organizational complexity. The second level recognizes that subsidiaries are themselves organizations and have their own levels of lateral collaboration depending on how hierarchical or flat the subsidiary structure is. Such variation in structures reflects, among others, locations, cultural, and institutional characteristics. The question asked here is about the effect of subsidiary structure on subsidiary performance. Finally, each subsidiary can concentrate the responsibility for the lateral collaboration in the hands of a single or few persons or distribute it evenly among all members. The focus here is on the effect of using boundary spanners on subsidiary performance. Here's how an MNE is modeled. Each MNE is composed of three subsidiaries, each with 7 members. K and C are the average numbers of other members on which a member depends internally and externally respectively. I use 3 different levels for each K and C. In terms of structure, X is the most hierarchical and Z the flattest, with Y in between. To test for the role of boundary spanners, 3 different levels of concentration of the lateral collaboration for each value of C were used. Overall, 27 different configurations were created. The table on the right shows the example of one. Now, on the operationalization of the structure flatness and concentration of lateral collaboration. I define flatness as the degree to which structurally similar members are connected with each other. To illustrate, consider the unit with 4 members shown on the left pane as a network or as an adjacency matrix. Arrows show the direction of influence. Each member is described structurally by its influence, or the number of outgoing arrows, and dependence, or the number of incoming arrows. Using influence and dependence, each node is depicted as a point in a two-dimensional space. The Euclidean distance between 2 points represents the dissimilarity of the members. Each element of the matrix A is multiplied by the corresponding distance, and the average represents the flatness index as per this equation. High values of the index mean that the structure is hierarchical, low values that it is flat. To measure the level of concentration of the lateral collaboration, for each unit I count the outgoing arrows to other units for each member and use a Herfindahl index as shown here. To illustrate the construction of rugged landscapes, consider again the small units from before with its adjacency matrix, where the column influences the row. Each member influences itself, and hence there are ones along the main diagonal. Each of x1 to x4 takes one of the two values, 0 or 1. So in total there are 16, 2 to the power of 4, positions for the unit as shown here. The payoff for a member choosing 0 or 1 is a number drawn randomly from the uniform distribution 0, 1. More on that later. It will be redrawn anytime the member itself or any of the other members on which it depends changes. So the payoff for x1 would be redrawn anytime x1 itself or x3 changes. These payoffs are shown here. The performance of the whole unit is the average of the contributions of its members as shown here. But the members of a unit may be connected to other units too. Here, the two units have a double arrow that connects them, and hence the rugged landscapes of X and Y are coupled and the units coevolve. To illustrate this coevolution, let's consider first unit X and keep Y2, the only Y element that affects X, fixed at 0. The left pane shows X's rugged landscape. The upper half of each oval is the position on the landscape, the bottom half its performance. The highlighted ovals are local optima. A link between two ovals means they are neighbors, or differ in one element only. An arrow shows the direction of performance increase. X starts at a random point, say here, and then moves to here. With no external influences, X would further move to here, here, and finally reach this point, a local, in this case also global optimum. However, in an NKC system, before X moves again, it's Y's turn to move. Assuming such move involves changing Y2 from 0 to 1, the landscape of X has changed to the one on the right. Importantly, the move X would have made, namely to get to this point, is no longer possible since it has inferior performance. Instead, it can move here, which incidentally is no longer an optimum. Now to the simulation rules. Each of the X, Y, and Z choose random initial positions in their respective landscapes and make moves in rotation. Each unit makes 100 steps, after which the performance is recorded. The results are sensitive to the randomness in both the initial positions and the generation of the performance landscape. To eliminate this effect, I repeat each round of simulations 1,000 times, starting at random points and generating random landscapes each time. The overall performance is the average of 1,000 values. Now to the results. At the M&E level, the variables of interest were K, the amount of inter-unit links, and C, the lateral collaboration. The table on the left shows the performances for different combinations. The one on the right, the t-tests comparing any two combinations. Two conclusions can be drawn. Looking at C relative to K, it's clear that combinations where C exceeds K are inferior, and hence the internal complexity creates an upper limit for the lateral collaboration. When we consider total complexity, that is K and C together, the medium-medium combination outperforms the other two. Based on these results, I propose that M&Es perform best when the level of between-unit collaboration is the same or lower than the level of within-unit collaboration, and when the overall complexity is moderate. Regarding the effect of subsidiary structure, the most hierarchical structure is significantly inferior to structures with medium and high levels of flatness across all KC combinations. The comparison between medium and high flatness structures is mixed. The medium ones perform better at high levels of internal complexity, the flattest at medium level. They perform the same at low levels of internal complexity. Overall, these results suggest that the amount of lateral collaboration within the unit is positively associated with unit performance. Finally, to the role of boundary spanners while keeping K, C, and structure constant. It turns out that concentrating the responsibilities for the lateral collaboration in the hands of few people is beneficial, and this effect gets weaker as the structure becomes flatter, leading to the following proposition. The level of concentration of the lateral collaboration has a positive effect on performance, and this effect is weaker for flatter structures. In conclusion, complex adaptive systems view of the M&E suggests several determinants for the success of lateral collaboration in M&Es. At M&E level, it's important to keep the balance between within and between unit collaborations, as well as the overall amount of complexity. Therefore, lateral collaboration shouldn't be considered in isolation. Its success is crucially related to within units collaboration. At subsidiary level, the flatness of the structure and the concentration of responsibilities for lateral collaboration seem to have a positive effect on performance. That concludes my presentation. Thank you for your attention.